There are these invisible rules that kind of run everything. I mean, think about it. From just flicking on a light switch to the massive, complex grid that powers our entire city, there's this hidden blueprint behind it all. It's like a set of instructions, and they're all written in the language of physics.
So here's a question for you. What do your glasses, the light bulb in your room, and the entire power grid have in common? I mean, on the surface, they seem totally different, right? But they're not.
Turns out they all run on this hidden blueprint, and it's made up of just a few simple but really, really powerful physics principles. So today, that's what we're going to do. We're going to decode some of that blueprint and see how just a handful of fundamental laws shape, well, everything from the power in our walls to the very glasses on our faces.
All right, first up, let's talk about one of the biggest problems we've ever had to solve: creating and harnessing energy. And it all boils down to one thing, really: generating a current.
Okay, so you've got two main ways to do this: AC and DC generators. Now, deep down, they're both doing the same basic job. They take motion, like a spinning turbine, and turn it into electricity. The real difference, the big one, is in how that electricity flows. AC, that's alternating current, think of it like the tide. It's constantly ebbing and flowing, reversing direction. DC, or direct current, is more like a river. It just flows steady in one single direction.
And that one little difference, it changes everything. AC generators use these really simple things called slip rings. They're smooth, they don't wear out much, which makes the whole thing super efficient and low maintenance. That's why they're perfect for all the stuff in your house, like your blender or your vacuum. But DC generators, they need something way more complicated called a commutator. It's basically a switch that flips the connection every single half turn to force the current to only go one way. All that switching causes a lot more wear and tear, but it gives you the kind of power you need for huge motors. We're talking about things like subway trains.
Okay, so we've got a current, great. But whenever that electricity moves through a wire, it creates heat. And it's easy to just think of that as waste, right? Just lost energy. But what if that waste, heat, wasn't a bug? What if it was a feature? One of the most useful things we've ever figured out how to control.
Yeah, this is all because of an elegantly simple idea called Joule's law of heating. The formula itself is H equals I squared RT, and what it tells us is exactly how much heat you're going to get. It all comes down to just three things: how much current you're pushing through, squared, the resistance of the wire, and how long you let it run. And because we know that, we can control the heat precisely.
And this law isn't just some random thing that someone pulled out of thin air. It's actually built from other things we already know. You start with a basic idea of electrical work, then you just plug in the definition of charge, and you plug in Ohm's law for voltage. You do a tiny bit of algebra, and boom, you get Joule's law. It's a perfect example of how physics works. It's like a set of Legos, where every piece clicks perfectly into the next.
And you use this principle literally every day. Your electric kettle, your toaster, even an old incandescent light bulb. That's all Joule's law in action. See? Each one of those has a special part inside with really high resistance, and it's designed specifically to take that electricity and turn it into a predictable, useful amount of heat, whether that's to boil your water, toast your bread, or make a filament glow bright enough to light up a room.
All right, so that's harnessing energy. Now let's switch gears completely and talk about bending light. I mean, what happens when the world just gets blurry? Well, it turns out physics has an answer for that too.
See, when your vision isn't quite right, it's really just a physics problem. The light coming into your eye isn't landing where it's supposed to, on your retina. And the solution to that physics problem is another physical object, a precisely calculated lens.
Let's break down the two most common ones. If you have myopia, that's nearsightedness, it means your eye is focusing the light in front of your retina, so things far away look blurry. To fix it, you use a concave lens, which spreads the light out just a tiny bit, pushing that focal point back to where it belongs. Now, if you have hypermetropia or farsightedness, it's the exact opposite problem. So you use the opposite solution, a convex lens, which brings the light together more strongly to get it to focus correctly. It's such a clean, direct fix, isn't it? A physical problem with a physical solution. And of course, the strength of that lens isn't just guesswork. It's all calculated using the lens formula. It's a fundamental rule in optics that tells you the exact shape you need to bend the light perfectly and bring the world back into sharp focus.
Okay, so we can correct our vision. That's amazing. But what about seeing beyond what our eyes are even capable of? What about seeing things that are incredibly far away or unbelievably tiny? Well, that brings us to our next big idea.
And that idea is called resolving power. Now, this is crucial. It's not just about making things look bigger, it's about making them look clearer. It's about an instrument's ability to tell you that two things that are super close together are in fact two separate things. Without good resolving power, two stars in the night sky just look like one big blurry blob.
So, where's the line? How do we know the absolute limit of what we can distinguish? Well, a physicist named Lord Rayleigh figured that out. He came up with something called the Rayleigh criterion. It gives us the exact mathematical point where two light sources are just resolved. Now, the definition sounds a little technical, I get it, but trust me, a picture makes it all make sense.
Okay, here we go. This image explains it perfectly. On the far left, you see two separate, distinct peaks of light. No problem, they're resolved. Now jump to the far right. It's just one blurry lump, unresolved. But look at that picture in the middle. That's the magic moment. That's just resolved. It's the exact point where the peak of one light wave falls right into the first dip of the other one. That is the absolute physical limit of clarity for whatever instrument you're using.
So how do we get better resolution? How do we see more clearly? Well, for a telescope, the answer is pretty straightforward. Just build it bigger. A larger diameter lens or mirror gathers more light, and that means better resolution. For a microscope, there's a really clever trick. You can use a medium with a higher refractive index, which is just a fancy way of saying something that bends light more. By putting a tiny drop of special oil between the lens and the slide, you can capture more light and, you guessed it, improve the resolution.
So, when you boil it all down, there are two big rules for getting better resolution. 1, make your aperture, your opening, as big as possible. And 2, use the shortest wavelength of light possible. And that second rule, that's the secret behind electron microscopes. They don't even use light. They use beams of electrons, which have these incredibly short wavelengths, and that allows them to see things that are way, way smaller than any regular light microscope could ever hope to see.
Okay, let's pull back and look at the big picture again. We've touched on generating power, creating heat, and bending light. We've basically been decoding little pieces of that master blueprint of our world. And think about what we've seen. In just a few minutes, we've looked at 4 absolute cornerstones of that blueprint. We saw how electromagnetic induction powers our lives, how Joule's law lets us turn that power into heat, how the lens formula literally brings our world into focus, and how Rayleigh's criterion tells us the ultimate limit of what we can possibly see. And to me, this is the most incredible part. You have all this complex, amazing technology, the entire power grid, telescopes that can see distant galaxies, microscopes that see individual cells, and underneath it all, what do you find? A simple, elegant, and totally understandable law of physics.
Just 4. We only talked about 4 core principles today. And with just those 4 ideas, we can explain so much of our modern world. It really shows you just how powerful a few fundamental truths can be.
Which, of course, leaves us with one last question to think about. What other hidden blueprints are out there? What other fundamental rules are shaping our reality in ways we don't even understand yet, just waiting for someone to come along and discover them?